Hello, my name is Danica Kurode, and this is the Constant Velocity Lab 1 in Physics 2211 in Professor Curtis's class. What I did today was record a sliding block on a track, and the goal of the lab is to compare the observed and predicted graphs in order to analyze velocity and the differences between both models. So model 1 was observational, where I analyzed the video I created through Tracker. Tracker allows us to analyze the real-life scenario of constant velocity, and model 2 was the predicted model, where I created a computational model using GlowScript, and this allows us to create an ideal model of constant velocity since the code uses the position and velocity update formulas without a change in velocity, so it's easy enough to put into code. Finally, I compared the two models to analyze velocity in order to find my result. So the fundamental physics principles I used were Newton's laws, Newton's first law being an object in motion stays in motion unless acted on by another force, and F equals ma. I also used the update formulas in order to put it into the code, and some basic information on forces such as gravitational, frictional, and normal force. So overall, the result was that the graphs were more or less the same, with some slight differences, which I'll get into later. So here is the model in the video that I made. So the system is the block and the surroundings are the track and the table. The initial conditions was that I gave it an initial velocity of 0.246 meters per second, which I found on Tracker. There was no acceleration, zero net force, and the position started at 0 meters. I assume a zero net force in order to create the ideal scenario, but the graph will show us that there is actually a slight acceleration, aka a force on the object. So here is the video. So as you can see, it was a block on a track with negligible friction between the wheels and the track. I pushed the cart once to give it an initial constant speed, and I recorded this motion to analyze on Tracker. So this is the Tracker analysis. You can see all the little points there, taking it at the same amount of frames each time, and you can see the graph that Tracker made, creating a somewhat linear line where it's comparing the X position and the time. Here is the code that I created. So I used the starter code and I made very minimal edits. I found the average velocity through the video and using two data points, and I put this velocity in as the initial velocity at ball.velocity equals vector 0.246, 0, 0, which is the second highlighted line I've shown. I kept the initial position at 0, 0, 0, which is the first highlighted line I showed. The third highlighted line shows the net force being 0 because this is an ideal scenario where constant velocity is happening, which means 0 net force. Ball.velocity, which is the fourth line that I highlighted, is equal to ball.velocity plus delta t times fnet, which is the velocity update formula. And the second one is ball.position equals ball.position plus delta t times ball.velocity, which is the position update formula. And I put the time as less than 5 seconds because my video went to about 4.5 seconds, so I wanted to make sure that the computational model had at least the same amount of data as my video. So here are the two lines that were created by the observed and predicted models. The observed model is the darker purple and the predicted model is the lighter purple. As you can see, the observed model data was slightly lower than the predicted model. So the predicted model basically created an ideal scenario where the velocity was constant throughout the whole time period, but because in a real-life scenario there is going to be some slight friction through the tracks, the observed velocity will slow down over time. Since we know that an object in motion stays in motion, since it's slowed down, we know that there is no constant velocity and that there was a force on the object. So all in all, the computer model is good for short sections of time, but the linear graph will not match the real-life scenario that will eventually slow down as time goes on. Some potential sources of error was the friction between the cart and the track, which was why the observational model did not match the predicted model. And because I pushed the cart by hand, it may have had some slight initial acceleration while the hand was still on the cart, and the track/table may not have been completely flattened, so there could have been a slope going up or down. What if the x-axis was flipped? So if the x-axis was flipped, the velocity would just be negative rather than positive. Since velocity is a vector, the speed would stay the same, the direction would just flip along with the x-axis. And for the what does it mean question, you can figure out the sum of the forces on an object by seeing the situation and the outcomes. In the y direction, there was no movement in the video, and we can assume that this is because the gravity pushing down and normal force pushing up caused a net force of 0. In the x direction, we can see that the observed velocity was lower than our computational model, telling us that there was some unbalanced force in the x direction. Potentially, this could be the friction between the cart and the track slowing down the cart because the friction overcame the constant velocity. And in an ideal situation, we know that since there is no force on the x-axis, the cart would keep the same velocity until acted on by some other force. Thank you so much for listening to lab number 1, and I hope you enjoyed. Bye!